Okay, so we started where we left yesterday. So we are doing the carry save multiplication, multiplication based on carry save addition, and basically landed up with a tree. Basically this is the 16-bit 8-bit multiplier which multiplies two 8-bit numbers and basically gives you a 16-bit number. And as you see, it is a tree of carry save adders. And some of the things that we learnt or that we saw yesterday, some of the things that we saw, some of the points that we noted yesterday was that if there are two n-1 bit and one n-bit number, the resulting two numbers that will come out of these three are n and n bits. n-1, n plus 1, we get n plus 1, n plus 1, n and n, we get n and n plus 1. So this is something that we need to keep in mind, and we use this particular stuff to show that when they multiply two 8-bit numbers, we do get 16-bit number. So typically here when I add 8, 9 and 10, I get 10, 10, 11, 12 and 13, I get 13 and 13. Then I add 13, 14 and 15, I get 15, 15. 13 and 13 and 15, I get 15 and 15, and so on and so forth. Okay, so when we add three 15-bit numbers, then we get a 15 and 16-bit number, and we add a 15-bit number to a 16-bit number, we get a 16-bit answer. So this particular whatever we saw here is extremely necessary for us for two reasons. First, to appreciate the point that two 8-bit numbers indeed gives us a 16-bit result, but then we can also do quite a bit of optimizations here, right? So let me just copy down those three here. So when I have n-1, n-1 and n, this gives me n and n. The next one is that n-1, n plus 1 will give me n plus 1, n plus 1. So I can just write it as n-2, n-1 n will also give me n, right? Both mean same, and n and n will give me n comma n plus 1. I think these are the three formulas that we need to keep in mind. Okay, so with this, these three were actually used to show the 16-bit answer, but now let us go and see how we can optimize it a bit further. Okay, so let us see how we can go and optimize this a bit. I will use a different color. Okay, good. So for this particular addition, please note that we need, so I have an 8-bit number, 9-bit number and a 10-bit number. Okay, so I need basically, let us say worst case I need 10 full adders for this carry save addition. So carry save addition is a collection of full adders in parallel, right? So in the worst case I need 10 full adders in parallel, but actually the last number, if you take the 10th bit here, it is basically 0, 0 and 1, okay, the 10th input to the 10th bit. Okay, are you realizing this, right? It will be 0, 0, 1. So I will be happy with just 9 full adders, because the last bit is anyway 1 and the carry bit is 0. So I can hard code that. So it is not that I require 10 full adders here, I could manage it with 9. So I am just optimizing one here. Now here I am taking a 11-bit number, 12-bit number and 13-bit number, but you please note that the last 3 bits are zeros for all, right? Because this M3 is an 8-bit number with 3 more zeros at the end. Now it is a partial product, right? When you look at the partial product, M3 is a 8-bit number with 3 zeros at the end. M4 is again an 8-bit number but with 4 zeros. M5 is again an 8-bit number with 5 zeros, right? So I again require, please note here that I could remove it is not that I need 13 full adders here. It is enough if I have 10 full adders, because the last 3 bits are 0. And also note that the first bit after that would have 1 0 0 or 0 0 0 whatever, right. The 11th M3 basically will have the first bit after it has 3 zeros and then it will have some A here. The remaining things are zeros, so I just need to take that A, right. So I can cut one adder there, so I can cut up to 4 adders at the front, and again at the last the first bit would be the most significant bit for the M13 will have 0 0 and whatever A, right. So I need not have one adder at the last and one adder at the beginning. So 3 plus 2, 5 adders I can get, so it is enough if I have just 8 full adders, right. Again here please note that even if I take that 8 bit number M0 will be, the first bit will be some A, and for M1 and M2 this is 0. So I need not have that last adder also, so I can manage this with 8 full adders. In same argument, so I do not need 10 full adders here, nor do I need 13 full adders here, I can just manage with 2 8 full adders, right. So let me again explain you in a little more whatever. So M0 will be some A0, A1, A2, A3, A4, A5, A6, A7. M1 will be again, let me say B0, B1, B2, B3, B4, B5, B6, B7. M2 will be, so this is 0. C0, C1, C2, C3, C4, C5, C6, C7. So this is 0 and this is 0, right. So you do not need an adder for here, right, to generate. So you know the sum bit is A0 and the carry is 0 already, and you do not need an full adder for this, right. So essentially you need only 8. So again when I take M0, M1, M2, when I take M3, M4 and M5, the partial products, please note that there will be 3 zeros for M3, again 3 zeros for M4 and 3 zeros for M5 already, and then you will have 7 number 1, 2, 3, 4, 5, 6, 7, 8. And I will have 1, 2, 3, 4, 5, 6, 7, 8. Then I have 1, 2, 3, 4, 5, 6, 7, 8. So I do not need an adder for this, for this, for this, for this, and also for this, right. These are easily, I do not need a full adder for that. So I need a full adder only for 1, 2, 3, 4, 5, 6, 7, 8. Are you able to appreciate this, right? So let us go back to the slide, right. So 8 full adders are sufficient for this, again 8 full adders for this, right. And now what happens, I get 2 10-bit numbers, okay, again, and here I am getting a 13-bit number, but there are 3 zeros at the end, right, and this is a 10-bit number. So there are 3 zeros at the end, so 10, 10 and 13. So again you can actually see that if you just work it out, I will just leave it as a simple exercise, you can finish off in 9 full adders, right, and so on. So ultimately if you sum up the amount of full adders, right, you will get very close to n log n, okay. So we can prove that in a very, so I just want you to work out for a 8-bit adder and just appreciate how this is going to figure out, okay. So though the circuit looks sort of big, but we can actually optimize it very carefully in the way we mix these numbers, okay. Now what is the depth of this circuit? how will you prove the depth of the circuit? How will you calculate the depth of the circuit? Suppose I am multiplying two n bit numbers, what is the depth of this circuit? How do you prove that? Any ideas? How will you go ahead and prove this circuit depth? Hey, you've done so much of data structures, man. Come on, can't you just see? What are the data structures you have done? CS, IIT Madras. Trees you have done? Hey, come on. Array, you do it in third standard nowadays. Okay? Trees, binary search trees, Fibonacci heaps. No. He says yes, you say no. What are the data structures? Can somebody tell? Kavya, can you tell me? What are the names of the data structures you said?
Stacks, queues, heaps, trees.
Then? What are type of heaps? There are many type of heap. Min heap, max heap, na. Other than that. Either you do it specific or not. It's not too specific, it's not half answer, it's binary, 0 or 1. Only heap. Then spanning trees. One semester you just did only till heaps.
Graphs.
What graphs? BFS, DFS. Means what? I am asking you. Okay. Right. Okay. So you did complexity analysis of this, right? For search trees and all. So did you do automatic balancing, auto balancing trees, like red black tree, AVL trees, red black trees? Okay. You have done so much. Come on, show this, man. This is trivial thing. Come on. Hello, Palakkad. What are things? What are data structures you all learnt? List of data structures that you learnt. Black shirt, first row. Yeah, correct yourself. Yeah.
This text use binary trees.
Then this is 1 week or 2 weeks max. Then after that. What is this, man? All of you have short-term memory loss or what? Okay, the yellow shirt behind. Yes, exactly. That much only you did that. We are doing now. Oh, data structure is in this semester. Okay, sorry. Okay, good. So correct, 2 weeks you have done 3 things. Yeah, very good. Okay, so you all did computational engineering, right? Yeah, you did binary search? Yes or no? Yes. So how do you analyze the complexity of a binary search? Suppose I am given an array of n elements. What is the time to query whether an element, whether a given query element exists or not in that array? What is the time required? Order log n. Okay. Now, how do you prove that? Let me just see. Now so I will not use h. Okay. I will use h. What happens is initially you start with n numbers. After the first step, what happens? You want to add n numbers, so you start with, let hn be the height of the tree. Let hn denote the height of a tree which multiplies two n bit numbers. So hn is height of Wallace tree, I'll just say wt, that multiplies two n bit numbers. Okay. Now what happens after one step? This n, so how many partial products you will have? So essentially you have n partial products to start with. So essentially Hn, let Hn be the height of W tree that adds n partial products, both are same, right. So let Hn also denote the height of the Wallace tree that shall add the n partial products or the n numbers, right. Now what happens after the first step? It becomes 2n by 3 and you are going to recursively do the same thing for that, right. That is what we have seen, right. So what did we see here? So we took the first step and we did whatever we did for the first step, the same thing we are continuing for the second step. So it is a recursive construction, okay. So Hn will now become h of 2n by 3 plus you have added one level. So Hn will essentially become h of 2n by 3 plus 1. So this falls into the equation of what we call as Hn is equal to h of n by a plus 1, a greater than 1, correct. So how do you solve h of how do I solve this? H of n is equal to h of n by a plus 1, h of n by a is equal to h of n by a squared plus 1. So h of n essentially becomes h of n by a squared plus 1, so plus 2, okay. So like this we can say that it is h of n by a cube plus 3, so h of n by a power k plus k. When this will stop? When n by a power k equal to 1 or k is equal to log n to the base a. So h of n is h of 1 plus log n to the base a, correct, correct. N by a power k becomes 1, k becomes log n to the base a. So h of n is equal to h of 1, h of 1 will be a constant, so h of n is, I can go and say it is order log n to the base a. Can you do that? Now let us go back to the previous slide. So we have a is 3 by 2. Yeah, sorry.
So how did you arrive at h of n equal to h of 2n by 3 plus 1? How did you get 2 by 3?
Huh?
2 by 3, h of 2n by 3.
So this you understood, this whatever, this slide you understood? Did you follow that h of n is equal to h of n by a plus 1, that equation? The answer for h of n is order log n to the base a. Did you understand this? Yes or no? Yes. Okay, so I will come to your question slide 1 minute in a minute. Now when I substitute a is equal to 3 by 2, right, this equation, both these equations are same. So what is the answer for this? H of n is log n to the base 3 by 2 plus 1. So which is again order log n, logarithmic in n. Okay. Now 1 minute. So I will come to your question very shortly. After bringing it to 2 numbers, right, then what we do? We again do a carry-Lucas addition. Now what is the complexity of carry-Lucas addition? I have again say I have 2n bit numbers, right, 2n bit numbers, it is again logarithmic in n. So the carry-Lucas addition also takes this plus CLA, which also takes again log n, log 2n is again log n, order log n time, like log 2n is log 2 plus log n, 1 plus log n, okay. So it basically takes this much amount of time. So the total complexity of multiplication is also order log n. right, right, it is all some constant times log n. Okay. Are you able to follow? Right. Now coming to his question, how did I get this equation, right? I start, so Hn is the height of the Wallace tree that shall add the n partial products. In one step, right, I reduce the number of, so it is actually n numbers, right, I am trying to add n numbers, each partial product is a number, I am adding n numbers. In one step, in the first step we have n numbers, in the second step what happens, I have 2n by 3 numbers, because every 3 numbers become 2, right. So if I have 9 numbers for example, then this essentially these 3 become 2, these 3 become 2, these 3, so I will have 6 numbers here. From 9 it becomes 6, right, do you understand this? And so I will have 2 numbers here, 2 numbers here. Now I can club these 3 and become, these 3 can become 2. So from 9 it became 6, from 6 it became 4. So n is 9, 2n by 3 is 6, right, 4n by 9 is 4, right. So every time I will get 2/3 of the number that is there in the previous level, because every 3 numbers now every triplet is converted into a pair, okay. You understand this? And that is how I get Hn is equal to H2n by 3 plus 1. Are you able to follow? Okay, good. Teacher feels extremely happy if the student understands, okay. Thank you. Now, is all clear? Are you able to follow? Now, let us look at some very interesting. So, why should I, so what is, so we say how in an architecture course, we just say that this is how Wallace tree is constructed, this is how addition is done. But we took some effort to basically tell you this takes log n time. So by showing that carry lookup adder is also log n, order log n, and multiplication and addition both can be done in log n time, what point did I drive you? What is the point that I am trying to drive here?
Till now, we like in all our computer science courses, we assume that addition and multiplication take the same number.
Exactly. So where did you make this? So in many of the courses, including data structures, suppose I say what is this algorithm and what is its time complexity? What is it? Tell fully. Okay. What is this algorithm? What is this? What does this piece of code do? Matrix addition. So what is the time complexity? Order n squared. What does this do? What is the time complexity? Now what assumption did we make here? That this multiplication is also constant time, this addition is also constant time. So we made an assumption here when we were analyzing the algorithm that multiplication and addition takes almost the same time, right. So when we are analyzing the complexity of algorithms, we do have something called a model of computation, right. We do have something called a model of computation, and we analyze the complexity based on the model of computation, correct, right. So one of the model of computation is called algebraic model of computation. This algebraic model of computation basically assumes that there are several things, that all this plus, star, division, subtraction all takes constant time. Accessing memory takes constant time. Like that it makes certain assumptions. And when you analyze the algorithm, you are analyzing it with assuming an underlying model of computation. If you say order n squared of what? Order n squared time. What do you mean by time there? N squared time means what? Time, who gives you that time? That is a model of computation which says that these are all the operations that will take unit time, and if I analyze using this model of computation, then my algorithm is n squared, right? If I use another model of computation, my algorithm may take some other time. Okay. So now, given that addition and multiplication are taking the same amount of time, almost the same amount of time, we are now justified in telling that, in actually stating that this is order n squared and this is order n cube. Able to follow? Correct? Right? Now there is some comparison that if I actually go and implement this in a real world machine, which basically has a carry lookup adder and a Wallace tree multiplier, then certainly we will get a very good the actual timing that you measure will be proportional to this n squared and n cube. Able to follow? Now this is the relation between architecture and actually relation between theory and practice. So we assume, we make certain assumptions in theory, and that is based on certain practical implementations, right? My algebraic model of computation is valid provided I use these type of arithmetic circuits internally. If I do not use these type of arithmetic circuit, if I use a Turing machine to add two numbers, then my arithmetic algebraic model of computation is no more valid. Okay? Are you able to see that thing where theory meets practice? Right? This is a very, very interesting and important example for all computer science and electrical engineers to understand, right? Now also keep in mind, so I want you to go and explore a bit. I am going to give you some extra reading, though I will not ask any exam. I do not plan to ask any questions in the quiz, but I want you to go and look at this finite universe model of computation. Okay. Please understand that the arithmetic that we do, the type of computations that we do on systems, it is not infinite arithmetic, it is finite arithmetic, correct? If I have a 32-bit architecture, the two numbers that I could add is maximum bounded by 32 bits. So if I go and add something more than 32 bits, I can't represent anything, a number which will take 33 bits here, right? So if I go and add more than 32 bit, then it becomes what? 0, right? So because the bits above 32 will be lost. The system does not have the width to hold anything beyond 32 bits. So if I am going to handle numbers which cannot be represented in 32 bits, I will end up with a overflow. So the system will tell I have a overflow, but then the result will not be there. It will, so if you keep adding 0, 1, so let me say it is a 3-bit system. So 0, 0, 0, 0, 0, 1, add 1, add one more, add one more, add one more. Now you add one more, you will go back to 0, 0. That one will be lost. But what the architecture will tell you, hey, there was a overflow. But then the result is lost forever. So this is so the systems on which we are working are basically finite arithmetic systems, finite addressable system. So the memory, if you have 32 bits, I can address maximum 4 GB of RAM. So it is not an infinite system, right? So so something which is very close to our computers today is this finite universe model of computation. So people have started working on this in 1980s, right, late 80s. So you can see a lot of papers and literature on finite universe model of computation. Just Google it and you'll certainly get a couple of wiki links. Just have an understanding of what we mean by finite universe model of computation. Okay. Now, so I have a model of computation that is realized by the hardware. Now, how does this manifest itself in the program? It manifests itself in the program through instructions, machine instructions. So there will be a machine instruction called add, there will be a machine instruction called mul. So you write a program in in the C language like this. This basically gets translated to some add, it's a machine language. This basically gets translated to this mul. So this program essentially becomes zeros and ones, and somewhere this plus will become add, and this add is now given to the architecture, and that will basically use the carry look ahead adder. This mul goes to the system and that will basically use the velocity multiplier, right. And since we use these fast circuits, this addition will take almost the same time as multiplication or vice versa. Okay. So this is how the entire system works. So this is very obvious, but you need to understand this obvious fact also. Okay. Fair enough, right. So so the last thing that I want to convey today, okay, so afternoon we have a lab. In the lab we will talk about basically how C programs can get translated into assembly code, right. So we will just basically take some programs and see how we can translate them to an assembly code. I will give you some examples of this, and we will also post the Intel manual which is close to 1000 pages. I do not want you to read those 1000 pages obviously, but then you can use it for quick referencing of there are 750 odd instructions. So you can quickly refer to some instructions so that you can start your first programming exercise next week. Okay. So today we will give you some translation from a C code to normal code. Okay. So what we will be doing next, I started asking some questions in 2's complement. I hope you all remember 2's complement. Yes or no? So we will just very quickly go through 2's complement in tomorrow's morning class, and then we will start division or floating point representation. One of this I will do. Floating point representation is extremely important, and specifically the IEEE 754 standard. Okay. Because that is the actually building bridge between engineering, computation, and computer science, okay, or electrical. Okay. And for ECE or EE students at Palakkad, you will be doing a lot of MATLAB work, you will be doing a lot of digital signal processing, fast Fourier transform. These are all going to be bread and butter for you in the coming semester, or probably you have done something in this direction earlier, and all of these are numerical computations. And so it is very, very important that you understand how these numbers are represented within the computer, and there could be truncation errors. So we will be showing you a lot of errors that could come in this entire business, right. So if you are not careful about handling floating point, that too because it is a finite arithmetic again, so you have limitations in number representation, then you will land up with so many stupid results, right. And you will also assume, if you are not careful in actually doing the computation, modeling the computation, we will show how you may get answers which are significantly erroneous. It is not that some 1 into 10 power minus 9 is the error, it will be significantly erroneous, right. And that error is sufficient enough. For example, a rocket takes up that and that you have written a program and it is all floating point, and something goes wrong there, that is enough to actually bend down the rocket and bring it back to you. So soon it comes and it is okay, right. So Actually, a rocket launch failure was due to a floating point. It's called a $1 billion bug. Okay, so because one rocket went up and it fell down, then the reason was a floating point error, and they lost $1 billion in designing that rocket. Okay, so that's called a $1 billion, $1 million or $1 billion bug, costly bug. Okay, so we will discuss about floating point, and you should understand that completely and thoroughly. Okay, thank you.